Hey, AP Chemsters, this is Mrs. Vanderlei bringing you Blankwalle, Chapter 11, Section 5, Part 2. And this is vapor pressure and dynamic equilibrium. So what is vapor pressure? It is the pressure resulting from the collisions of the vapor molecules. How's that? Kind of go back to Chapter 5 again. And dynamic equilibrium, that's kind of a new term. We're going to talk a whole lot more about equilibrium a little bit later on in Chapter 14, I believe. And what does this actually mean? Dynamic means moving or motion. Equilibrium, that means the rate of the forward reaction equals the rate of the opposite reaction or the reverse reaction. So when we're going to see things like that? Well, hang on and we'll talk about it, okay? So if a container is left unopened, the liquid will all evaporate. Why? Well, it's what we said before. If you have a beaker of water and you leave it open, eventually it's all gone, right? A couple of things are going to happen. Depends on the temperature. If you have a hot temperature, then it's going to evaporate quicker, but it still will all evaporate. What if you had a large surface area? Then it's going to evaporate pretty quickly, and it depends on the strengths of intermolecular attractions, right? So if a container is left open, why does it all evaporate? Well, we're going to talk about here, it all depends on temperature. So for this question, the rate of evaporation depends on temperature. All liquid molecules will have enough energy to become a gas in the temperature range of that liquid. If it's too cold, become a solid. So eventually, all those liquid molecules will rise to the surface, right? And will have enough energy in that liquid phase to become that gas, okay? And if it's not in that liquid range, it's too cold, and then you get a solid. So that's not going to be an issue. But then what? This is the next question. This is what we're going to talk about. What if the container is sealed? And I think of a terrarium. Okay, maybe you made one for your mom when you're in elementary school. Okay, you get a big container, you stick some soil in it, you stick a couple plants in it, you give it some water, and then you seal it. And what happens? You never have to water that terrarium again. Why is that? Because the liquid that will evaporate will later condense and re-water your plants again. How cool is that? Try it if you've never seen it before. All right, and so that's what's happening here. So look at this picture, isn't this cool? So what happens? You just put the liquid in there. You have no vapor in there, okay? So the only thing happens at the surface, some of these will become a gas. That's what those blue arrows mean. So now we have created a gas, okay? And what can happen with some of these gas molecules? They are in close proximity. They could bump into another gas molecule, form that, attraction, hey baby, and then they're going to recondense. So by this time, notice we have some molecules evaporating and some molecules are recondensing. And that's what this is all about, okay? So the water begins to vaporize, that's in the first one, and then as the water molecules build up into the gas state, they begin to recondense into a liquid. Why? Because of attraction, okay? They're in close proximity, they are bumping into each other, they have the opportunity to have that connection, that attraction again, and will become a liquid. And then eventually the rate of evaporation will equal the rate of condensation. And I want to show you this picture up here. This is a really important picture. We're going to see this later on in, let's say, Chapter 14, and we talk more about equilibrium. So where do we begin? We're going to start here. This is the rate of evaporation. Let's say we have, 5 molecules per second. That would be a rate of evaporation, and it remains fairly constant. And so we have right here 5 molecules per second are becoming a gas. But what's down here? This is my first beaker, is like in the beginning. There are no gas molecules, so you don't have any condensation. No gas molecules are becoming a liquid. But what happens is more and more gas molecules because like in the second you have 10 molecules. In the third second, you're going to have 15 molecules. So what happens as time goes on, you're going to have more and more gas molecules in that gas phase, more opportunity for those gas molecules to be attracted to each other, and voila, you're going to make a liquid. Until eventually, at this point right here, you're going to have the same 5 gas molecules becoming a gas, and those same 5, or not the same, but 5 gas molecules then recondense into a liquid. So that is what we call a dynamic equilibrium. So let's see what this says here. Rate of evaporation is the same as the rate of condensation. Vapor pressure depends on is the pressure of the gas in dynamic equilibrium and depends on the intermolecular attractions. Why? Okay, what have we talked about so far? Well, the stronger the intermolecular forces, what's going to happen? What if these have really, really strong attractions for each other? Are you going to get 5 gas molecules per second? No, you may only get 1. Okay, so then I have fewer gas molecules up here. All right, and if I have fewer gas molecules, then I have less pressure. Okay, and that's kind of what I wrote down here. The stronger the intermolecular force, the fewer gas molecules are present. Fewer gas molecules means fewer collisions, less pressure. So the weaker the IMFs, that means they're going to be more readily making a gas. So you're going to have more gas molecules present, meaning you're going to have more collisions and you have greater pressure, okay? So if you need to pause this to finish writing, why don't you go ahead and do that? Otherwise, I'm just going to move right on, okay? So what can I do to change this equilibrium? Well, again, we're talking about pressure, aren't we? So what are some things that can change pressure? Well, volume can change pressure, right? So, what's pressure? Let's talk about that. Pressure is force per area, right? Do you remember that? So if volume increases, initially the pressure will decrease. But now you have more liquid molecules will evaporate until there is the same pressure as before. So if the area increases, the force collisions must increase to keep the same pressure. And well, guess what? If volume decreases, it's the opposite. If volume goes down, there is less area, so pressure will increase initially. So more gas molecules will recondense until there's the same pressure as before. And so that's what these pictures here are showing you. So if I just keep this steady, okay, we're going to have the same number of molecules as before. But what if I open up this, okay? So if the gas or the volume is increased, initially pressure is going to fall, okay? Now you have more room, if you will, for more gas molecules to vaporize, and then you can have that same pressure again. So down here, if volume is decreased, then initially pressure is going to go up. So then you're going to have more gas molecules in closer proximity. That attraction can happen. The more condensation is going to occur, and then you're going to have the same pressure as before. And so what this is saying that if I change a condition, this equilibrium is going to react in a way to reestablish what it was before, okay? And that's kind of what's called Le Chatelier. And again, we're going to talk a whole lot more about Le Chatelier later on, okay? But Le Chatelier, he's a French dude, by the way, said that when a system is in dynamic equilibrium is disturbed, okay, like changing the volume, the system responds so as to minimize the disturbance and return to a state of equilibrium. So in the case of increasing the volume, all right, pressure initially falls. Oh no, it's been disturbed. Well, what can the system do to reestablish that pressure? You're going to have more rate of evaporation. What about over here? What if you decrease the volume? Oh no, you've disturbed the equilibrium. The pressure rises initially, but then it's going to make more condensation and the pressure remains as before, okay? So look forward to this in chapter 14, okay? Problem 14, though, says what happens to the vapor pressure of a substance when the surface area is increased at constant temperature. So what's going to happen? Well, let's think about this. Let me scroll down a little bit. I didn't talk about vapor pressure. I just talked about rate of evaporation and rate of condensation. So what happens to the vapor pressure of its substance when its surface area is increased? So what happens? You have more evaporation. If you have more evaporation, you have more gas molecules. If you have more gas molecules, guess what? You're going to have more pressure. So the vapor pressure will increase. Okay, let's go to the next page. Okay, this is a really important section. Temperature dependence of vapor pressure and what? And boiling point. So, maybe we'll answer that question of what's the difference between evaporation and boiling, okay? All right, so when temperature of a liquid increases, the vapor pressure increases. Why? Well, what's happening to your system? You're getting more energy to that system. So go back and think about that video I showed you on part 1. Remember that? Those gas molecules are looking like they're in a mosh pit or something, aren't they? Okay, so what happens when more molecules are given more energy? Guess what? You're going to have more gas molecules, or I said that totally wrong, didn't I? What happens when those liquid molecules are given more energy? They're going to have more molecules are going to become that gas. Okay, so if I have more gas molecules, vapor pressure increases. All right, as temperature increases, the vapor pressure increases, more energy is added, so more molecules are able to break their IMFs to become a gas. More gas molecules means more vapor pressure. So what happens eventually? As temperature goes up, vapor pressure goes up. Okay, so more pressure, okay? So what is the difference between evaporation and boiling point? Well, boiling point is the temperature where the liquid molecules become a gas at what? At standard pressure, okay? At standard pressure, okay? So this graph is really kind of a cool graph, okay? The boiling point of a liquid at the temperature at which a liquid's vapor pressure equals the external pressure. The thermal energy is enough for all molecules. Hey, let's underline that one or do something, okay? Let's highlight that. For all molecules. What molecules? All. Interior and the surface to break free. So what's vaporization? When the surface molecules break free. What's boiling point? When all molecules, internal and surface, okay, will break free of their neighbors and enter the gas phase. So the normal boiling point, this is different than number 1, all right? The normal boiling point is a temperature at which its vapor pressure is 1 atm. The boiling point of a liquid of the temperature is with the liquid's vapor pressure equals the what? External pressure. The normal boiling point is when that vapor pressure is 1 atm. Okay, so look at this here. Here's the normal boiling point. That's where you have 760 torr, which is 1 atm, and there's the boiling points. Well, what happens if you are on top of a mountain? Okay, so then maybe the external pressure is down here. Well, look at the graph, all right? So what happens if you have a lower ATM? I just made a line here. Tell me what happens in each of these cases. Do you have a higher temperature or a lower temperature? Oh, it looks to me it's a lower temperature. So wait a minute, what are you telling me? That if you're on top of a mountain, that water boils at a temperature less than 100 degrees Celsius? And the answer is yes, that is true, okay? So that's what this graph is saying, okay? Why is that? Because it's the external pressure equals the vapor pressure is when it boils, okay? So like I said, you add more temperature, more energy, you make more gas molecules, so there's more collisions, pressure goes up. That's why each one of these lines are going up with temperature, because you're getting more and more particles in that gas phase, okay? So it says, as long as a liquid is present, temperature cannot rise above 100 degrees at 1 atm. You remember this graph? We did this already, okay? So when you're having a phase change, the temperature will not change until all of those liquid molecules break free and become the gas. So here we can say, if this is, let's say, water or something, that this is where it's all liquid. Here I have all liquid. Here I have a mixture of liquid and gas. Here I have all gas. And once that last liquid molecule is gone, now the temperature of those gases continue to rise, okay? So it says, why do recipes have special instructions? All right, so let's find out. I think I already said that. At high altitudes, the atmospheric pressure is less than 1 atm. The boiling point will be less than 1 atm, just like the one I showed you with the line up here, okay? So this looks to me to be a good place to quit for now. The part 3 is going to do some math. We're going to learn about the Clapeyron equation, which we're going to have a lab upcoming all about. So make sure you have a calculator and don't wait to be great. See you shortly. Bye-bye.